And the next presentation is by Bergh, who will tell a story about interface of two semiconductors and the impact of the interface of two semiconductors onto modern technology.
It's not harder to press buttons when you're looking over your hands. Okay, so I get to talk about semiconductors and their uses in transistors. So transistors, they're in your phones, they're in pretty much every electronic device ever, and they're basically brought to life by the use of these semiconductors. So basically what a semiconductor is, it's two different, it's an element that has some movable electrons in it, but not completely like metal. And a transistor involves a p-n junction. It's kind of like the heart and soul of the on and off switch for the transistor. So there's a p-type and there's an n-type, and they're generally made out of silicon. And you can basically you can dope these with different doping atoms. Like the n-type, you would dope it with phosphorus because it's about the same. It has an extra electron. And p-type, you dope it with like boron, so it actually takes an electron out, so it creates a hole. So this is basically what, or that's what makes like the light switch of the transistors. So this image is basically telling us how a transistor kind of works. So basically on the boundary between the two different semiconductors, your n-doped, so your negatively doped semiconductor has an excess of electrons in it, and your positively doped has a lack of electrons in it. So it's got a bunch of holes. So at this barrier, there's a certain distance where these electrons are going to disperse over and fill the holes in the positively doped semiconductor. So in this area right here, this is called the depletion zone. So this is actually depleted of movable electrons and movable holes. So when these electrons move over here, it actually creates a negative boundary on this part and a positive boundary on this part. So it creates an electric field. And then so this would be like a graph of like voltage and the electric field and what the charge has to encounter when you're trying to pass a current through it. So this is an image I pulled off of YouTube, but it's basically just illustrating the positive side and the negative side of the interface. So the next slide right here, this is basically talking about the strength of the depletion zone on the interface. So it basically relies on two different things. It relies on the voltage applied to the outside of the transistor, so that what the voltage does is it decreases the size of this depletion zone by this equation, or the potential difference of the current itself. So basically, it's like the kinetic energy of how much current you're pushing through it to basically push your electrons past this negative barrier through the transistor. Right? So yeah, so basically the one that I tested was just increasing the kinetic energy, increasing the momentum of your electrons going through your barrier, as opposed to the voltage decreasing the depletion zone. So basically kind of what it has to get over is this is like your n-type, and what that image is showing is kind of like confined within the n-type, as long as you have a lesser amount of kinetic energy. So,
Mouse.
I'm not pressing
Mouse.
any buttons. There we go. So basically what this one is showing is that I have my kinetic energy, I have my momentum set at negative 0.5 right now. So it's not very energetic pushing through the transistor, so it stops right at this barrier, right here. So it's confined to your one type of semiconductor. And then this one, I bumped it up to negative 1.5. So the energy level is actually above the potential difference of your field at the interface. So this one just flows right through it. It's got an open current moving through the transistor. So.
Okay, well, thank you.